everybody. How you doing? Thanks a lot for coming to see me. This is a little bit about me. My name's Josh. I've been at Cloudera for about a year or so now. Before that, I was at a company called Google. My first job there was working on the ad auction. So if you do a search on Google, ads show up. Maybe you click on them, maybe you ignore them, all that kind of good stuff. That was me. You're welcome. Anyway. After that, I worked on a team that built a whole bunch of data infrastructure. A lot of it got used in Google+, a lot of it got used in Google News, a lot of it got used in mobile search. Everything from logging, dashboards, friend recommendations, and experiments, which is what I'll be talking about today. Before my Google time, I spent a little bit of time as a software engineer, I spent a little bit of time as a statistician, and I studied math at Duke, and came awfully close to finishing my PhD at the University of Texas before I kind of came to my senses and got out of there. So yeah, all right. Let's see, this is the data science Venn diagram. You guys are probably all familiar with this. This is the idea of what is data science. It's this combination of computer science, math and statistics, and something called substantive expertise. And it's the substantive expertise that I want to focus on today. Sort of in the question of how exactly does one go about acquiring substantive expertise? What does substantive expertise mean when we talk about data science? So my claim is that experiments are what lead to expertise. What a data scientist does is typically study a very complicated system. And a complicated system could be a search engine, could be an ad network, could be a social network. Systems that are basically too complicated to really reason about a priori in any kind of regular way. And when systems become that complicated, we have to do experiments on them in order to understand sort of their principles and how they operate, right? Fairly classic problem at a lot of big companies is the hippo problem. You guys haven't heard of this. This is the highest paid person's opinion. How decisions get made is the highest paid person's opinion. And experiments can be somewhat scary for organizations because they're all about sort of toppling the hippo problem. The sort of famous example of this is Greg Linden. If you guys know Greg, machine learning guy. When he was at Amazon back in '99, he came up with this cool idea for saying people who bought this might have also bought this, like sort of product recommendations, right? And his plan was to insert these recommendations in between, basically during the checkout phase of an Amazon. Like basically you're going through, getting ready to check out, let's offer you some recommendations from other products. And there was a VP at Amazon who was like, no, absolutely not. You never ever interfere with people who are about to make purchases. You can't do this, I forbid it. But this is Amazon, it's a bunch of nerds, so Greg and his friends do it anyway. And obviously it turned out to be like massively, massively profitable for Amazon, like right away. They could tell after a day or so that it was gonna make them all kinds of money. So highest paid person, not right all the time. Everybody has good ideas and experiments are about taking advantage of that. The other problem is that sometimes users don't actually know what they want. The great example of this is Marissa Mayer gave a talk once where Google did a survey and they asked people, would you like to have 30 results per page? Would that make you happier? And people were like kind of overwhelmingly like, yeah, 30 results per page, that sounds awesome. I would really like that. So they ran an experiment to see how that would work. And the metrics were awful. They were absolutely terrible. And the reason was because the implication of having 30 results per page is that queries took something like 100, 200 milliseconds longer to fulfill and render on the page and all that kind of stuff. And in general, anything that makes anything slower is bad for usage. It's the easy rule of thumb at Google. Fast is good, slow is bad. So even though people thought they wanted it, when you actually tried it out and see what the implications were, it turns out to be kind of terrible. People hated it effectively. All right, okay. So when we talk about large-scale experiments, what are we talking about today? Hundreds of treatments, tens of millions of subjects per treatment. It's kind of cool. Anytime you want, you can pretty much start an experiment at Google, and within 2 hours, you'll be running an experiment on 1 million people. You don't really need to ask anyone's permission or anything like that. It's pretty cool. And you have billions of observations that you want to analyze. So hundreds, millions, billions. Very, very large-scale stuff. All right. It turns out that this kind of scale requires some of the sort of rethinking of approaches that we did in computer science in terms of building very large-scale systems. The same sort of rules kind of apply to statistics. I've interviewed a lot of PhDs in statistics in my day, and my problem was typically that a PhD in statistics teaches you how to extract anything you can from a very small quantity of data. And that's basically never my problem. My problem is, how do I not be confused by an enormous quantity of data? It's basically the exact opposite, right? So usually when I'm interviewing people, I'm looking for an understanding of the fundamentals of like probability and statistics, like a very fine-grained understanding, because I sort of am going to have to teach them everything from the ground up in a way. Just the stuff they know is not necessarily useful for me. All right. So let's talk a little bit about how an infrastructure for doing experiments. Mostly what I'm talking about in this talk is a couple of different papers. The first one we're going to talk about is one by Diane Tang, Ashish Agarwal, Mike Myers, and Deirdre O'Brien. And I know all those names so well because they used to be my coworkers. Diane was my boss. And this is about the experiment infrastructure at Google that's used for search and advertising. A couple of terms, just so you guys know for the rest of the slides. We have search queries. That's a request. Each request comes with a cookie. And there's maybe some sort of conditions we want to apply to this request. We might say, there's some features of the request we know. We know there's a country associated with it, there's a language, there's probably a browser, that kind of thing. All these conditions, all right. And we're interested in trying out different settings for parameters on the system. And some easy examples of that are, what is the ad background color? Is it pink, is it yellow, is it blue? Is Google Instant on or off? That kind of thing is what we're talking about. We also have controls and experiments. So every experiment has to have a control, otherwise it's not a particularly good experiment as a sort of thing. And we want to make sure that the controls and experiments have matching diversion criteria. So if the experiment is only interested in people in Russia, the control should only be against people in Russia as well. I hope that makes sense. Okay. All right. A/B testing. A/B testing is a marketing term. Don't say A/B testing. Say multivariate experiments. That's what we say. We're engineers. That's what we do, right? We don't do A/B testing. We want to do A/B testing quickly. So all of Google's systems, and I like to think every software system everywhere, is parameterized in some way. You have per server settings that are basically fixed for the life of a particular binary, right? What's my master? What port am I listening on? That kind of stuff. These are per server attributes. And we also have per request attributes that we're interested in changing on a request by request basis. And that might be, what color should the ads background be? What machine learning algorithm should I use? All these different parameters in the system that we want to be able to change basically at will. And these are the parameters we're going to be experimenting on, okay? Always, 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 we want to push data and not code. To run an experiment, we really ideally want to push a very small data file or make a database update instead of having to go push an entire server binary, right? The system has to have two features. One, obviously, is it has to be able to divert traffic on a consistent basis. I have to be able to take a cookie and make sure that it receives the same treatment over and over and over again for some period of time. The other one is that I want to log everything. I want to associate in the log records what experiments plural, a user was in, even if the condition that I was interested in experimenting with didn't trigger on that particular request. So for example, a user in the United States might be in an experiment for people who speak Spanish. If they don't type in a Spanish language query, my experiment won't trigger, but I still want to know the person was in the experiment. That makes sense. Okay. So back in the day, it's like 5 years ago, it's forever. The single layer, all right. Google had a system where for every request, it was in at most one experiment, right? Very straightforward system, very easy to analyze, no conflicts, but basically things didn't scale, as you can imagine. Google kind of rapidly ran out of traffic space. They had too many experiments and not enough traffic. This is kind of a problem, right? As much search growth as you have becomes the limitation on how fast you can innovate. You end up creating smaller and smaller experiments in order to kind of squeeze more things in there, but that doesn't really help you because it takes longer to get statistical significance, right? This is kind of a problem. So what do they want to do? Google is a very data-driven company. A lot of companies say they're data-driven. Data-driven is kind of like big data. It's like so overused as to be meaningless at this point. Data-driven really means decisions are made based on metrics. Ideas are evaluated primarily based on how they perform, all right? So basically, Google's ability to innovate is limited by how many experiments it can run at the same time, effectively speaking, right? So what do they want? They wanted more experiments. They wanted better experiments. There were a couple of cases, I wish I could talk about them because they're really funny, of cases where Google did not interpret experiment data properly and made bad launch decisions. Decisions that either cost them money or result in a worse experience. It's okay. Find me later, get me drunk, that kind of thing, we can talk about it. They also want to be able to do experiments faster. Very easy setup, get results essentially in real time, and run their experiments on enough data that they achieve statistical significance quickly. All right, so how do you do that? It turns out to be kind of cool. What they did was they took the original layer and they basically created a whole bunch more layers. So each layer has a hashing function associated with it. Basically, it's a single hashing function, and each layer's identifier is the seed for the hashing function. And what we do is when a request comes in, it gets diverted into an experiment in every single layer. So any given request at Google is actually in 10, 12, 15, 20 experiments at the same time. It's kind of cool. I know it seems kind of crazy. How does it work? The idea is that experiment flags, the kind of per request flag settings you can change, are divided up into logical groups, and each logical group belongs to a single layer. The reason for that is we have to have a page that we can render. So if I have like the add text, there's a parameter control of what color should the add text be and what should the add background be. Those two things can't be set to the same color because then you can't actually see the add text, right? That would be bad. So that kind of thing. So for instance, like all the ads user interface stuff is in a layer. Search has multiple layers. The ads machine learning stuff has multiple layers. All these things are varying independently of each other. Okay? Works out really, really well, as it turns out. And actually, the way you can tell is this great. This is actually the graph from the paper, and in typical Google fashion, there's no y-axis. But this is the growth in both the simultaneous experiments and the number of people running experiments over time. That little dashed line is when they put the new system in place back in 2007. Those dips there you see, kind of like post 2007. Those are holidays. Google, December, you just turn off experiments for all intents and purposes. Just let the system crank and make money, that kind of thing. Okay, so I have a good system for deploying experiments. I'm really happy. How do I go about analyzing experiments when I'm dealing with the sort of the volumes of data Google deals with? A couple of just very core basic concepts here. Hypothesis testing and confidence intervals. Most of the stuff we're going to talk about today is about confidence intervals, but we're talking about confidence intervals, but we're kind of referring to a hypothesis test in some way. So we're comparing to an experiment and a control, and we're interested in knowing whether or not some particular metric we're interested in is roughly different from zero, right, in the significance testing sense of the term. And the way we're using that is whether or not the confidence interval for the ratio of those two terms is significantly different from one. Or the difference of the two is significantly different from zero. That's the idea. Okay. Most of the time, most people don't actually interpret confidence intervals correctly. I'm sure you guys have had statisticians harangue you about this for years now. It's not the probability that the parameter is not within that interval with 95% probability. That's not what that means. It means that if you sort of hypothetically reran the experiment 100 times, 95 of those times the parameter would appear in that interval. Turns out to be not the same thing, and people usually sort of say one when they don't really quite understand it. A lot of the metrics we care about in the web are ratio metrics. So click-through rates, right? Cost per click, all that kind of stuff. Typically ratios. And we're typically interested in the percent change in these ratio metrics between experiments. So how much did the CTR change between treatment A and treatment B? That kind of thing, right? But it turns out that calculating confidence intervals for ratio metrics is actually kind of hard. Because in particular, if I have two normally distributed random variables, the expectation of their ratio is actually undefined. The ratio of these things has a Cauchy distribution, which is, bad. So we need some methodology that allows us to come up with reasonable, sensible confidence intervals while sort of dealing with this problem, effectively speaking, this sort of undefined expectation problem. In order to move quickly, we also want a dashboard, and we want it to largely automate all the good stuff we want when it comes to analyzing experiments. So our desirable features, obviously we want a valid methodology for calculating confidence intervals. Very important. If we don't have that, we don't really know if these two things are different from each other. We want drill down, like we would in any dashboard. Like, show me these two experiments, split them up by country, split them up by language, split them up by web property, anything like that. And also, for better or worse, we want the metrics to update in essentially near real time. I spent a lot of days at Google just kind of sitting there clicking the refresh button on the experiment dashboard every 15 minutes to see the new numbers on my experiment. It's kind of, it's a thing where it's your idea and you're trying it out and you kind of get personally invested in it. And you know you shouldn't do it. You know you should wait 24 hours and wait for the metrics to be significant and all that kind of stuff, but you can't help yourself, right? It's just like too much fun to watch. All right. This is one of those great choose two kind of problems. What is it? It's the fast, good, cheap. It's choose two. Is that kind of thing? Or is it choose one? Whatever. Anyway, this is the same problem. In order to properly compute confidence intervals accurately, I actually need to have all of the data available to me in order to do things properly. And this can be an experiment that runs over months and months and months of data, right? If I want to see how does cranking up the number of ads someone has shown influence their likelihood of clicking on ads over time, some sort of longitudinal study, it can be like months of data that I would need to analyze. And having to analyze that much data in order to correctly compute the CIs basically directly conflicts with those other two things I want, which is real-time updating and support for interactive drill downs. So if I didn't have to do drill downs, I could basically have a big table instance that had all the data in it, and I could just kind of map reduce over it periodically, and I could compute everything and make it available in a cache for lookups. But when I started wanting drill downs, I have this problem of essentially combinatorial explosion, right? All the different dimensions that I possibly want to drill down by have to have their own kind of like bucketing and aggregation done, and the whole thing just, kind of sound, basically, on your computer. So that doesn't really work for me. So we need some other solution to get around it. And the thing they came up with is actually a statistical trick, as it turns out. And it's called the index method. So I can't keep running aggregations, at least of a single bucket for the experiments I care about. But what I can do is keep B buckets, where B is some number, realizing right now that B was not the best choice for this variable name, but nonetheless. We have these B equally sized buckets. And we basically, as each request comes in, it gets partitioned into a bucket based on the cookie that is associated with the request. So it's basically an orthogonal hashing function, taking mod 20 or mod 25 or whatever, and each request goes into a different bucket. And then I can compute the metrics I care about on each of those 20 different buckets, and then perform a two-sample t-test, and then basically, boom, I have a confidence interval, just like that. It's about as easy as it gets, right? Couple of tricks with this. So there's some sensitivity to the underlying distribution of data. In particular, if you were at a very unprofitable website and the revenue tended to be very close to zero, your confidence intervals would probably not make sense a lot of the time. If you're dividing by very small values, you can imagine things tend to get out of control relatively quickly. And there's a different technique you have to use when that happens called Feeler's method. There's a great paper by Franz. It's really all about ratiometrics. Sorry, I think ratiometrics are basically the coolest thing ever. Anyway, I would just go read this paper for fun, and I recommend you do it too. The other thing is that my confidence intervals are not quite as narrow as they would be if I had actually computed the z-test properly by using all the data. But it's actually pretty close. So if I use 20 buckets, I'm basically 93% as efficient as I would have been. So the idea is the confidence interval is a little bit wider than it would have been otherwise if I'd done things properly. But I get to basically aggregate the data. It only costs me 20 times what it would have if I was doing the simple aggregation trick. I get all my slices, and I get the metrics updated in essentially real time. So I'm certainly given the volume of scale of data that Google has. 93, 94% efficiency is pretty great. It's not a huge problem, right? So two other things I wanted to talk about really quickly. Oh, I'm totally rocking it on time. This is great. Okay. All right. So I'll just talk about these things for 20 minutes or whatever. First and foremost, power of counterfactuals. You ever find a statistician? Statisticians love counterfactuals, right? If I have two search algorithms or two recommendation algorithms and I want to figure out which one of the two is better, one of the best things I can do is just throw out any observations where they give me the exact same answer. That's not a useful observation in any sense. That would not have influenced anyone's behavior in any way, right? So I can just completely dispose of that and focus only on the observations where they actually give me different answers and see how that influences the behavior. So I can get a much greater statistical power in my tests much faster by doing that. The consequence of that, especially at large scale, is resource overhead. I have to execute my machine learning algorithm or whatever twice on all of my different input data, which can potentially be very bad. There's also a sense in which some of these systems can be indeterminate, non-determinate, non-determinate, right? Non-determinate? Yeah. No, it's indeterminate? Okay. One of those two words. So in the case of indeterminacy in the system, like if the RPC doesn't come back for one of the requests, something like that, that can ruin my counterfactual, which is kind of bad. Another thing that's great for search results and for recommendation systems is interleaving results. So a lot of the problem you have with experiments that are basically done on rankings of things is if you give people a set of results, they'll probably click on something, right? They're basically bored. They don't have anything else to do. So you may not necessarily get a real feel for which of these two algorithms is more interesting unless you actually take the results of both of them and interleave them together. Basically go, here's the first one from this one, here's the first one from this one, so on and so forth. And then you keep track of which results people interact with. Which ones do they like? Which ones do they click on and go away from? And you essentially credit those results to each of the different algorithms. And again, this is a fantastic way to get a much greater statistical power on your experiments than you would have by doing two separate experiments, like a traditional multivariate test. Okay. Things I'm kind of glossing over. I'm glossing over just so many things here. But in particular, two problems that don't really have great formal solutions yet, at least that I know of. If someone has solved them in this room, like please come find me because I would love to know what they are. Super common, multiple comparisons. Right? Everybody knows about multiple comparisons. If I have 100 different metrics that I'm looking at and I have a 95% confidence interval, then 5 of them will be statistically significant without actually really being statistically significant, right? And usually I have a lot more than 100 metrics I'm looking at the same time. So multiple comparisons is a real problem. Simpson's paradox, the other great problem. If I basically slice data in different ways, I can get sort of slightly counterintuitive results. Things like that well, the famous one is the Civil Rights Act. Think like if you look at it naively, Democrats were less likely to vote for the Civil Rights Act than Republicans, but if you slice the data based on whether the senator came from the North or the South, you see that Southern Democrats essentially voted against it en masse, and the rest of the Democrats voted for it, almost 100%, right? This is the sort of idea of like, you get different results depending on the way you slice the data, Simpson's paradox. The way we got around this at Google, the way it kind of worked out, is back to this notion of substantive expertise. You basically got people who it was sort of like, like the scene in The Matrix where the guy's watching the screen, kind of like filter down and it just makes sense to him. You know what I mean? Like it's blonde, brunette, redhead, that kind of thing. It's kind of like that with the ad system at Google. There's this big dashboard of metrics and you kind of get good at seeing the way things change or how things relate to each other. Like what typically happens when the CTR goes up, what typically happens to the CPC? How does that fit with what I know about what the experiment is doing, right? And I was trying to think of a term for this behavior, and I called it, it's basically a de facto Bayesian approach. You have a prior in your head that is your understanding and your model of how this system works. And you use that prior as a way to judge basically how real a result is. My favorite thing to happen when someone joined the ads team was for them to like look at an experiments dashboard and say, I don't believe that number. People who did it's like, that number is like 6% positive, but there's no way that's real, right? They basically they gained enough expertise to not be relying exclusively on the data. And that was kind of a really cool thing. I hope that made sense. I hadn't really come up with that idea before. I was curious how that would go over. Anyway, substantive expertise gained over time. Trust your data, but trust but verify for data. There's probably some pithy phrase here. I just can't think of what it is. In any case, questions? Thank you all very much. So the question was, how do you bound or how do you come up with reasonable experiments? How do you explore the parameter space? So a lot of the things that I was working on, a lot of experiments I was working on, were typically parameter settings for like how do I basically take this mixture of machine learning models, combine it, like basically weight them together to come up with a quality score. That was the kind of stuff I was doing. And there's a whole sort of methodology of study with it, and its name is escaping me right now. And I feel kind of bad, but it's been like 4 years since I've done this. But essentially you would create, based on like whatever your center point was now, whatever the current parameter settings were, you would create a sphere of parameters around it. So if you think of like a three-dimensional parameter space, you know, like vary this one this way, vary this one this way, and then a couple of others. And from those, from the results of all those different experiments, like there might be 20 of them, 30 of them, you could essentially interpolate and figure out an optimal parameter space for what you were looking for. That was generally what we did. Okay. Yeah. Yeah. Sorry, the question was, were these experiments always set up by people, or did machines ever come up with them? Yeah, we definitely experimented with, for parameter tuning and stuff like that, having the machine do it for you, basically go explore the space. But I mean, it would still be a thing where someone had some broad idea in some sense, and you were maybe just trying to tune or optimize. There's sort of like two ideas of experimentation, right? There's optimization, like I just want this to be better, and then there's understanding, like I'm actually trying to reason about the system going forward. And so generally you would throw the machines at the optimization problem, but people would still be interested in like the substantive expertise and the understanding side of things.